War is humanity's worst idea. It destroys cities. It divides families. It leaves scars that last for generations. But when the world goes to war, something strange happens. Science starts moving faster. When survival becomes the only goal, scientists get a rare kind of freedom, an unlimited budget and no time to waste. The Second World War was the biggest engine of invention in human history. Jet engines, computers, penicillin, even duct tape, all born from desperation. And one invention, in particular, changed everything. Radar. A machine built to see the invisible. It helped Britain survive its darkest days, and later, it helped create something you probably use today. The microwave. This is the story of how a weapon of war became a tool for peace. How scientists racing to save lives ended up transforming everyday life. This is wartime science, from radar to the microwave. It's 1935. The world is between two wars, and in the skies above Europe something new is taking shape. Airplanes are getting faster, bigger, and deadlier. If another war comes, and everyone can feel it coming, there will be no warning sirens early enough to save cities. Britain needs a way to see the enemy before the enemy can see them. Robert Watson Watt was a Scottish scientist who spent his career studying storms. He tracked lightning using radio waves, listening to the electric echoes of weather. He was a man of data, not warfare. But one day the Air Ministry asked him a strange question: could radio waves be used as a weapon to destroy aircraft? Watson Watt thought for a moment. Then he said no, not to the idea of using radio to kill, but to destroying planes with energy alone. However, what if radio waves could detect planes instead? That shift, from offense to observation, would change the future of warfare and science forever. He and his assistant Arnold Wilkins set up a field experiment in Daintree. They placed a transmitter on one side of a field and a receiver on the other. A biplane flew through the beam. The signal on the receiver's screen fluttered. That flutter was proof: the radio waves had bounced off the plane and returned. They had seen through the air. Within months, the British government moved fast. They built a series of tall towers along the southern and eastern coasts, each sending out radio pulses and listening for echoes. This system was called Chain Home. It became Britain's new eyes. Operators sat in rooms full of equipment, reading the screens and plotting the position of approaching aircraft by hand on large maps. When the Battle of Britain began in 1940, Chain Home gave the Royal Air Force something priceless: time. Radar gave pilots minutes of warning before enemy bombers arrived. Those minutes decided who lived and who died. Radar didn't fire bullets or drop bombs. It simply informed. And information was a weapon of its own. But early radar was huge and limited. The signals were long waves, needing massive antennas and stationary sights. They could spot planes coming over the sea, but not guide aircraft in real time or fit inside a fighter. Scientists needed to make radar smaller, stronger, and more precise. That goal would lead to a tiny copper block that changed everything: the cavity magnetron. At the University of Birmingham in 1940, two young physicists, John Randall and Harry Boot, were trying to create a better radar transmitter. Existing devices couldn't produce enough power at short wavelengths. Randall and Boot experimented with a copper block carved with small circular holes, cavities, that could resonate like a pipe organ. When electrons passed through a magnetic field inside this device, they created microwave energy, high-frequency waves strong enough to detect smaller targets with pinpoint accuracy. They had no idea just how valuable this device was. The cavity magnetron could make radar portable, more accurate, and far more powerful. It was one of the most important scientific leaps of the war. But Britain faced a problem: it could design the magnetron, but not produce it on a massive scale. The nation's factories were already stretched by bombing and material shortages. So the British government did something unexpected: they shared their biggest military secret with another country. A delegation of scientists and engineers, the TIZAD mission, sailed to the United States in September 1940 carrying a small black box. Inside was a magnetron. They called it the most valuable cargo ever to cross the Atlantic. When American scientists at MIT opened that box, they were stunned. The magnetron produced 100 times more microwave power than anything the US had. That moment ignited a new partnership, one that would turn a British invention into an Allied superweapon. This partnership led to the creation of the Radiation Laboratory at MIT, often called the Rad Lab. It grew from a handful of scientists to thousands of engineers, technicians, and researchers. Together they developed more than 100 types of radar systems for aircraft, ships, and ground operations. They shared their discoveries with Britain and Canada almost in real time. Factories across America, from Raytheon to Westinghouse to General Electric, began turning out radar sets in the tens of thousands. What started as a British experiment had become an industrial network spanning an ocean. It was scientific cooperation on a scale the world had never seen. By 1942, radar was everywhere. It was guiding ships through fog, helping pilots land at night, and directing anti-aircraft fire with deadly accuracy. In the darkness of war, humans had learned to see without light. And in the process, they had built the foundation for the modern world. When Britain handed that small copper block, the cavity magnetron, to the United States in 1940, it wasn't just trading a secret, it was sharing survival. The magnetron could generate microwave energy powerful enough to make radar small, sharp, and fast. Britain could design it, but it didn't have the factories to build thousands. So the TIZAD mission crossed the Atlantic with one goal: find partners who could turn prototypes into production. American scientists at the newly formed MIT Radiation Laboratory, the RAD Lab, opened the British package and realized they were holding the most advanced microwave source on Earth. Within weeks, US engineers were copying the design, improving it, and feeding results straight back to their British colleagues by telegram and diplomatic pouch. The war had created an international research team before the term even existed. The RAD Lab grew from a few physicists to more than 4,000 people. They built radar systems for every environment imaginable: airborne interception sets that let fighters hunt bombers at night, compact units for ships, centimetric radar for submarines, ground mapping radar that could see coastlines through cloud. Factories owned by Raytheon, General Electric, Westinghouse, and dozens of smaller firms worked around the clock turning out magnetrons by the tens of thousands. For the first time, science was industrialized at a global scale. Ideas passed from Cambridge to Boston to Ottawa and back again faster than ever before. In the process, scientists learned new ways to collaborate: clear diagrams, standardized connectors, and documentation that anyone could follow. Those habits would later become the foundation of post-war research networks and, eventually, modern electronics manufacturing. But this cooperation was not only about machines, it was about people. Young engineers fresh out of university found themselves solving life-and-death problems. Mathematicians calculated the geometry of radar dishes, chemists designed waterproof coatings, radio operators trained to read the faint echoes on flickering screens. Every improvement meant more soldiers and sailors would make it home alive. By 1943, Allied radar had changed the rhythm of the war. German U-boats that once hunted in darkness now found themselves illuminated by invisible beams. Convoys zigzagged safely across the Atlantic under the watch of radar-equipped patrol aircraft. In the Pacific, US Navy ships could track incoming planes long before they appeared on the horizon. Radar didn't just guide weapons, it guided strategy. The magnetron was the quiet heart of it all, spinning electrons inside its copper cavities, converting electricity into pulses of microwaves that traveled through waveguides to dishes and antennas. It was a masterpiece of practical physics, created in urgency but built to last. And in one Massachusetts factory, an engineer named Percy Spencer worked among those magnetrons every day. He didn't know it yet, but he was about to notice something small, something that would pull radar out of the battlefield and into every kitchen on Earth. By 1943, the pulse of the war had changed. The Allies were no longer fighting blind. They could now see, through fog, through night, through the sea itself. The whisper of radio waves had become one of the most decisive sounds of the conflict. In the skies over Europe, night fighting had always been dangerous guesswork. Pilots flew by instinct, hunting shadows. But radar changed that. Small units built around the magnetron were fitted into fighter aircraft. Operators in cramped cabins stared at glowing screens that painted the sky in light and echo. They could now lock onto enemy bombers invisible to the naked eye. The first successful night interceptions gave new confidence to the Royal Air Force and later to US air units. For the first time, technology, not luck, was guiding pilots in the dark. On the ground, radar helped guns find targets they couldn't see. In coastal batteries, radar directed anti-aircraft fire with such accuracy that enemy pilots began to speak of ghost gunners, crews who could shoot through cloud and smoke as if they had eyes everywhere. In truth, those crews were following a pulse reflected from metal wings thousands of meters away. At sea, the change was even more dramatic. The Battle of the Atlantic had been a slow war of attrition. German U-boats hunted convoys at night, rising silently to strike. Every ton of lost cargo meant fewer supplies, fewer lives. But by 1943, Allied patrol aircraft carried radar sets that could detect a submarine's periscope at astonishing distances. The hunter had become the hunted. In one 6-month period, U-boat losses doubled. The captains never knew how their positions were found, they only knew the ocean was no longer safe. Radar also transformed the Pacific. In the vast spaces between islands, ships once blind in darkness now tracked aircraft and enemy fleets over the horizon. Task forces sailed confidently through fog, amphibious landings were guided with precision. On the bridges of destroyers, young officers watched the sweeping line of the radar scope and felt, for the first time, that they truly knew what surrounded them. And radar reached into the airfields too. Landing in bad weather had always been a pilot's nightmare, but by the end of the war, approach radar let control towers see an aircraft's position and guide it safely down. Every life saved by that quiet beam was a victory in itself. The new science reshaped tactics, command, even language. Words like ping, echo, sweep entered daily speech. Generals talked about blips on the screen as naturally as soldiers once talked about lines on a map. The ability to sense without sight changed how leaders thought about distance and surprise. It was a revolution of perception. Yet behind the success lay exhaustion. Radar operators worked endless shifts staring at dim green screens, straining to tell the difference between a storm cloud and an incoming squadron. Scientists in windowless labs adjusted circuits and soldered joints until their hands ached. Every breakthrough demanded new labor, new sacrifice. They knew that the better their machines became, the sooner the war might end. When victory finally came in 1945, the world was full of inventions that had been created for survival but were now waiting for a new purpose. The magnetron was one of them. Millions of people owed their lives to the technology it powered, yet peace left it suddenly homeless. What could a generator of microwaves do in a world without bombers to track? Factories slowed. Research labs began to close. And in one of those labs, at Raytheon in Massachusetts, an engineer named Percy Spencer was still surrounded by magnetrons. He had built them, tested them, and repaired them throughout the war. They were familiar companions, humming quietly on the workbench. One day, as he stood beside an active radar set, he noticed something odd. The chocolate bar in his pocket had melted. At first he thought it was the heat of the room. Then curiosity took over. He placed a few popcorn kernels near the magnetron. They popped. He tried an egg, it exploded. He laughed, not at the mess, but at the realization forming in his mind. The same microwaves that had found enemy planes could also cook food. That moment of curiosity connected two worlds, the science of war and the comfort of everyday life. It showed how discovery never truly ends with conflict, it only changes direction. Soon, Spencer's experiments would give birth to a new machine, one that turned invisible waves into heat for homes and restaurants. The war had taught humanity how to see without eyes. Peace would teach it how to use that sight for life instead of survival. The war was over. The world had survived the greatest conflict in human history, and the weapons of technology were being packed away. But not every invention would rest. Some would quietly start new lives, far from the battlefield. In Massachusetts, Percy Spencer returned to his usual work at Raytheon. The factory that had once produced radar equipment was slowly shifting to peacetime research. Rows of magnetrons still hummed on benches, their copper surfaces glowing faintly under fluorescent lights. Spencer wasn't a university-trained physicist. He had left school early, taught himself mathematics and electronics, and built a career through curiosity and stubborn persistence. During the war, he'd helped perfect radar systems used on Allied ships. Now, with peace restored, he was one of the few people who truly understood the magnetron's power. One morning in 1945, as he tested a live radar set, something strange happened. He felt a sticky mess in his pocket. His chocolate bar had melted. It wasn't hot in the room, and the machine wasn't leaking heat, at least, not the kind of heat you could feel. The only thing coming out of the radar set was invisible energy, microwaves. Spencer was intrigued. He placed a handful of popcorn kernels near the magnetron's opening. Within seconds, pop, 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 they burst into fluffy white flakes. He laughed and tried again, this time with an egg. The egg exploded. The scientist inside him couldn't resist experimenting further. The engineer inside him saw opportunity. He built a small metal box, sealed it, and directed microwaves inside. When he placed food in the box, it cooked in seconds. The world's first microwave oven was born. At first, Raytheon's executives didn't know what to do with it. The machine worked perfectly, but it was enormous, over 5 feet tall and weighing more than 300 kilograms. It was called the Radarange, named after the radar systems that inspired it. Restaurants and ocean liners bought a few, amazed that food could be cooked almost instantly. But most people had never heard of microwaves, and the price, around $5,000, was out of reach. Over the next 2 decades, engineers refined the design. Smaller magnetrons replaced the bulky wartime models. Safety shielding and timers made the ovens practical for home use. By the 1970s, mass production brought prices down, and the microwave oven became a normal household appliance. From war room to kitchen counter, what a journey. The same energy that once found bombers in the night sky was now reheating leftovers. But radar's influence didn't stop there. The same principles, radio waves, reflection, measurement, spread into countless technologies: air traffic control, weather forecasting, automatic doors, and even the sensors in cars that prevent collisions. Radar taught humanity how to see using invisible energy, and microwaves taught it how to harness that energy safely. Every beep of a microwave is an echo from that wartime laboratory. Every radar image on a weather forecast carries the DNA of a system born from fear. The war ended, but the science never did. The war had ended, but the ideas it set in motion were still moving. The machines built to defend nations began defending something else: the future. After 1945, the world faced a strange silence. For the first time in years, the factories were quiet, the skies empty of enemy bombers. Yet inside those same laboratories the work continued. The scientists who had once built radar, magnetrons, and navigation systems turned their attention to peace. They didn't stop inventing, they simply changed the questions they asked. Radar's principles, sending out radio waves and measuring their echoes, proved useful in almost every new technology that followed. Civil aviation adopted radar first. The same screens that once tracked fighter squadrons now guided commercial airliners through fog and storm, keeping passengers safe. Airports built towers filled with spinning dishes, and the radar ping became the heartbeat of modern flight. Meteorologists saw another opportunity. During the war, radar crews had noticed that rain and snow could appear on their scopes. What had once been clutter now became valuable data. Post-war scientists refined radar into a tool that could map storms, measure rainfall, and warn cities before hurricanes arrived. Every weather forecast that shows a swirling cloud pattern is a direct descendant of the chain home stations of 1940. The military applications didn't vanish, of course. Radar became smaller, faster, and more precise, guiding jet fighters, missiles, and satellites. But its civilian children multiplied even faster: traffic control radar, ship navigation radar, speed guns, even the sensors that opened supermarket doors. Humanity had learned to live with invisible eyes watching helpfully from every corner. Then came communication. The magnetron's microwaves carried more than echoes, they could carry information. Engineers discovered that high-frequency radio waves could transmit voices, pictures, and data across continents. The same physics that once spotted an aircraft led directly to microwave relay towers, television broadcasting, and, later, the antennas that feed today's satellites. When space exploration began, radar was there too. NASA used radar to track rockets, to map the moon's surface, and to guide spacecraft home. Decades later, the same science would evolve into GPS, a network of orbiting transmitters allowing anyone, anywhere, to know exactly where they stand on Earth. A technology born from fear had become one of trust. Meanwhile, inside homes, the microwave oven spread quietly from novelty to necessity. Early adverts called it cooking with radio. Housewives and engineers alike marveled at food heating from the inside out. By the 1980s, hundreds of millions of microwaves were in kitchens worldwide. Few users knew that every hum, every warm plate, was powered by a magnetron nearly identical to the one that once pulsed inside a wartime radar set. Beyond the machines themselves, wartime science left another legacy: the model of teamwork. The cooperation between Britain and America, scientists sharing secrets instead of guarding them, became the blueprint for modern international research. Out of radar grew new institutions: the US National Science Foundation, CERN in Europe, collaborative weather networks, and the very idea that knowledge moves fastest when borders don't stop it. The people who built radar rarely called themselves heroes. Most returned to teaching or industry, quietly proud that their work had helped end the war. Robert Watson Watt went back to civilian science, eventually knighted for his contribution. John Randall and Harry Boot continued their research in physics. Percy Spencer stayed with Raytheon, guiding engineers who had once built weapons toward technologies for peace. Their inventions, and the way they shared them, shaped the world we live in: the radar that keeps aircraft apart, the microwaves that cook our food, the satellites that connect our phones. They remind us that progress is rarely simple. It can emerge from tragedy, yet serve kindness. It can start with survival and end with comfort. In the noise of war, they listened for echoes. In the silence that followed, those echoes became our modern world. If you enjoyed this story and want to hear more about the discoveries that shaped our world, make sure to subscribe to the channel. Hit the like button, it helps more people find these stories. And if you'd like us to cover another hidden invention from history, leave a comment below. Your curiosity keeps this channel alive, and together, we'll keep uncovering the inventions that changed everything.